English.
Yes, please.
Yes, please.
So last time we saw the connection between expansion properties of a graph and its spectral geometry or its eigenvalues. So let's just set again the notation. X, a finite graph. A equal A of X is the adjacency matrix. Okay, so this is usually a matrix with just 0 and 1. We don't care if there are multiple edges, then we don't mind that there will be other numbers, but usually just 0 and 1. And let's say the nice case, or the theory is slightly nicer, if X is K regular, then K is the largest eigenvalue with multiplicity 1 if X is connected, if and only if X is connected, and minus K is an eigenvalue if and only if X is bi-partite. Have we talked about all this? And you showed it? What?
I did not mention this last time.
What, the bi-partiteness?
Bi-partiteness.
Okay, so let's see just a very quick proof, because this kind of argument we'll need it later on in a slightly. Take a K-regular graph, and then let's assume first that it's bipartite. Okay, so if it's a bipartite, which means that there are two parts, and all the edges are going from one side to the other. Now I claim first of all that the size of the two parts must be the same. Why? Because if this part is, say, V1 and this part is V2, then if I count the number of edges going out from the left-hand side, then this is V1 times K, because the degree of every vertex is K. And if we count the same edges as coming out from V2 to the other side, then we get V2 times K, and therefore V1 is equal to V2. So if you have a bipartite K regular graph, then the sizes should be equal. Now, if we take the function f to be f of x is equal to 1 if x in V1, and minus 1 if x is in V2, then you can easily see that a of f is equal to minus f, minus k times f. This is trivial to check, because what is a of f? A of f is really summing up, because what is really a of f? The adjacency matrix, the way it out, that's very important to remember it like that. A of f of x is really sigma over all the neighbors of x of f of y. So in this case, you see that a of f is minus k. Let me point out something, that not only that k and minus k, but moreover, the spectrum is symmetric. Moreover, in this case, the spectrum, the set of eigenvalue of A is symmetric, i.e., if lambda in the spec, then minus lambda is also in the spec. Well, I guess I said it, or we are said it, that this is a symmetric matrix, so all eigenvalues are real, so we're thinking about real eigenvalues. And I want to declare that in this case, if lambda is in the spectrum, then minus lambda y, because it's basically the same argument, if f is in L2 of x, which means L2 of v, of v equal v1 union v2, with a of f equal lambda f, then let's define f bar of x in the following way. It will be equal to f of x if x is in v1 and minus f of x if x is in v2. And now you see that a of f bar is equal minus lambda times f. Times f bar. This is the same argument as I said before with the constant function. Basically, I took here the constant function. This f is the f bar of the constant function 1, 1, 1, right? And just like there, if you take the constant function, you get eigenvalue k. If you take this function, you get minus k. In general, if you start with an eigenfunction with eigenvalue lambda, then if you define f bar in this way, you will get that the eigenvalue is minus lambda. Right? This is clear, okay? Everyone sees this. It's okay? Okay, now what you saw last time, you saw a connection between the notion of expander and the difference between the largest eigenvalue, which is k, to the second to largest eigenvalue, which comes after that. Sorry, let me prove the other side. This is kind of proving the other side, that if it's a bi-partite, then minus k is an eigenvalue, and in fact the spectrum is symmetric. Okay, in fact, okay, let's assume now, minus k is an eigenvalue. Then let's define v1 to be all v in v so that f of v is positive. And yeah. And no, okay, no, I don't need this. I mean, I'll do it after that. Define v naught to be the point. V naught is a point, a vertex with f of v naught in absolute value maximal, without loss of generality. F is an eigenfunction. It's an eigenvalue with eigenfunction f. Let's assume that that's what we have. Then I take a point which get the maximal value. And without loss of generality, we can assume that f of v naught is positive, because if it would be negative, I can replace it by minus f. Minus f is also an eigenfunction with the same eigenvalue, right? Because this is a subspace. And then look at the neighbors. So we have v naught, and now v naught has k neighbors, and a of f v naught, a of f at the point v naught is sigma on f of y is a neighbor of x naught, Okay, so on one end this is equal to minus kf of v naught. On the other end, this is sigma of all the neighbors of y of f of y. Each one of them is an absolute value less or equal f of v naught. Right? So in absolute value, minus k f a of f of v naught in an absolute value is less or equal k times f of v naught. On the other end, we know that it's equal in absolute value to k f v naught. Okay, so really what I have to say, so the conclusion is that each one of f of this and f of y must be equal to minus f of v naught for every y which is a neighbor of v naught. It's okay. Maybe I didn't write it in the most elegant way, but you see, I'm summing up here numbers so that in absolute value, each one of them is at most f of v naught. And when I sum them all, and there are k numbers here, because this is the k regular term. If I sum them all, I'm getting minus k times f of v naught. Which means that in absolute value, each one of them must be equal to f v naught, otherwise it would be strictly less than k times f v naught. And it must be minus f v naught, because eventually I got minus k times f v naught. Okay, now, and so what we can see, and now we can continue like that. It's clear, right? So you see that we have here v naught, then that the value here is some positive number, and then the value in the neighbors will be negative of the same thing, but of the same absolute value. And then we can continue like that. The neighbors of this will be the same one like that, etc. Right? So you can see that this is and continue like that to deduce that we have v1 is all v such that f of v is equal to f of v naught, and v2 will be all v so that f of v is equal minus of v naught, f of v naught, and this will be two parts that all the edges will go to one part to another. That's a kind of a simple argument. You can complete it by yourself. I don't know, just start it on. Let's see if I wanted to say something more about this case before we go to the slightly more complicated case. And yeah, all the eigenvalues are in absolute value at most k because of the symmetry. You know, we know that the positive one is at most k. That's you probably showed, right? That the largest eigenvalue is k, and exactly k. There is nothing larger than it, and therefore there is nothing smaller than minus k. If you want to write this something. Okay. Now I want okay. There is something which is called mixing lemma for graphs. But I want to take a slightly a variant of it that we really need without doing the standard mixing lemma. The standard mixing lemma basically tell you, assume you have a graph X, which is an expander. Okay, the second eigenvalue is strictly less than the first one in some bounded way. Then if you take two subsets A and B of the graph, the mixing lemma basically tell you can evaluate how many edges are there between the two subsets. They don't have to be a set and its complement for any two subsets. I want to do a variant of it which will be needed. So ideally could do both of them with the same proof. The proof is similar, so I don't find it necessarily to do. And I'll do the one which we really need, which is really for a bipartite version. So let's do the following. So assume now X is a K prime, K double prime, bi-regular, bipartite graph. So by this now I mean that we have two sides, V1 and V2. They are not necessarily of the same size. Maybe I'll call it K1 and K2. They are not necessarily of the same size. So the degree here on this side is K1, the degree here is K2 of every vertex. Okay? So the sizes are not the same this time. What we get, if we count the edges, is we get that K1 times V1 is equal to K2 times V2. This is the connection between the sizes. And what we would like to do is to evaluate the number. Okay, maybe let's say a few things even before that about this graph, about the eigenvalues. So let A be the adjacency matrix of this graph. What can we say about it? Like, what is the largest eigenvalue? So here is one plane. The largest eigenvalue of A is square root of K1 times K2 to spec A is symmetric, namely a lambda eigenvalue if and only if minus lambda eigenvalue. So in particular, minus of square root of K1, K2 is also an eigenvalue. Okay, maybe we need a little bit more, then along the way we'll add some. Okay, so why this is true? Well, I did all the introduction actually, not in order to remind you, but in order to use it now. Because the easiest way to prove this is by analyzing the following graph. Let's look. I hope you know that maybe this is a general remark. I mean, any graph in A, the symmetrics of it, if you look at AX to some power L, then what you have in the IJ entry of this power, what you have is exactly the number of paths from I to J in A of length exactly L. It's the number of ways to go from I to J by a path of length L. And by a path we mean everything, like maybe also going back and forth or whatever. We need it only for L equal 2, but it's kind of cute to know it for in general, so I leave you as an exercise. But for L equal 2, so this would be exercise. But take L equal 2, that's the most important case for us. And you see that when you have a meeting like that, when you multiply the rows in A with the columns in A, you will get a contribution of 1 exactly when you can do a path of length 2 from I to J. So, okay, think about that. Okay, so now let's see, so back to our case. Now what we have here, we have a V1 here and we have V2 here, and we have K1, the degree here is K1, the degree here is K2, and what is A squared? I claim that A squared, we know what is A squared, right? It's the number of paths of length 2 from a point to point. I claim that A squared will look like that. In fact, you see, if you have a bi-partite graph, by the way, then the form of A is always something like that: 0 here, some B here, some B transpose here, and 0. Why? And I mean, this is not a square. This is like, this is, let's see. I have, you see, I take here, this is V1, size V1, this is V2. This is V2, I think so, right? Or maybe I should take the other way around, let's see. I take,
That's V1.
what? V1 here?
Here also.
What?
No, if it was V1.
Ah, yeah, V1 to V1, sorry, I'm sorry. Yeah, V1 onto V1, V1 onto V2, yes.
There's no edges from B1 to B1.
So B is a matrix V1 cross V2, the size. And it represents, it tells you when you have an edge from I on V2 to J of V2. And BT, if you think about it for a second, you see that what you get is simply the transpose of it, which is on the other side. And so what is A squared? A squared counts for us the number of paths from X to Y, from a vertex X to vertex Y, but path of length 2. But path of length 2 in such a bi-partite graph can go only from V1 to V1 and or from V2 to V2. So A squared, you can think about it either geometrically or either combinatorially or algebraically. Algebraically, if you multiply these two matrices, then what are you getting here? You are getting BBT, and here you get BTB, and here you get 0 and 0, right? Notice that these matrices are not of the same size. Right? This matrix is V1 cross V1, and this one is V2 cross V2. Okay, and we also understand it combinatorially because the entry here will tell you in how many ways you can go from a vertex here to another vertex here by two forms. How many here connect them, in how many ways you can go like that. Maybe with more than one way. By the way, in this A square, we have fairly large number on the diagonals. Why? Because I can go from here and come back, and I can go here and come back. So on the diagonal, we will see here, the diagonal here will be what? Will be K1, right? And the diagonal here will be K2 along the diagonal. Do you see this? because I start with V1 and I can have K1 ways to go and come back to the same vertex. Is it okay? By the way, here is another remark. Here is a trivial linear algebra lemma. Lemma BBT, that's always, if you take a matrix, not necessarily a square matrix, you take BBT and BTB have the same eigenvalues up to multiplicities of zeros. Namely, if you have an eigenvalue of this matrix which is not zero, then you have this is also an eigenvalue of this one, and vice versa. Well, the proof is not difficult. Let's say that if alpha is a vector, let's say that B is a matrix which is n over m, then if alpha is in, say, r to the n, and say BTB of alpha, right? This is n by n matrix is equal to lambda alpha. So this means that BTB of alpha is equal to B lambda alpha is equal to lambda B alpha. Then it means, that B alpha is an eigenvalue of BBT is an eigenvector. It's an eigenvector of BBT if lambda is not zero. Well, if lambda is zero, if it is not zero, if this vector is not zero, actually, if B alpha is not zero. But it's possible that B alpha will be zero. If it's not zero, because we don't count the zero vector as an eigenvector. If it's not zero, then we see that BBT of B alpha is lambda B alpha, which means that this is an eigenvector with eigenvalue lambda. So we started with a vector alpha, which is an eigenvector with eigenvalue lambda. And we found also a vector which is an eigenvector to BBT, right? We started with BTB and now we have to BBT, but now if B alpha is zero, then it really means that lambda must be zero. Because then simply B alpha is zero. So only the eigenvalue zero does not go from one matrix to another. And this argument is of course symmetric. I prove it to BBT, but it's the same proof for BTB. So it goes also from the other direction. That's okay? So they have the same eigenvalue. So now why I'm telling you all these things? Because now we can use it to analyze the eigenvalues of this bi-partite graph, because you see, let's look at A squared. So A squared actually represent two connected graphs. I mean, the graph which is represented by A squared is not connected because it has a block here which was what? BBT or BTB? BTB?
No.
BBT? BBT and here BTB. So you see, this is an unconnected graph because all the vertices here are connected between themselves and all the vertices here are connected between themselves, and There is no connection between the two. So there are two connected components. So the largest eigenvalue appears twice, and the smallest eigenvalue appears twice. But let's look at our largest eigenvalue first. So what is the largest eigenvalue? When we can think of this BBT, I claim that K1 times K2 is an eigenvalue of A squared for the constant function, with the function equal 1 as an eigenvector. Why? Because just think about it. What A squared does, you take a function on the graph, which is 1, 1, 1 on everything, and then you sum up for a point here, you sum up on its neighbors. What are its neighbors? All the elements for which you can go in 2 steps. So how many elements I have in which I can go to them from this point in 2 steps in the original graph? I have K1 to this side and then K2 to the other side. And this includes coming to itself. I'm allowing this will be a graph with many loops, but that's fine. I said before that I don't care about multi-edges or loops or all these other things. Is it clear? It's a simple poem, but somehow I feel I should say it. Is it clear? Or I lost you on this? I mean, don't get lost on this trivial thing. So this is an eigenvalue. In fact, with multiplicity 2, because the graph is not connected, I really can take the function to be, I can really take f1 to be the function which is 1 on v1 and 0 on v2, and f2 is the other one, 0, 1 on v1 and 1 on v2, and each one of them, a square of fi, is k1 times k2 times f1. So this is an eigenvalue, and this is and this is and really a square is a k1 k2 regular graph. You can really think of it as representing a graph which is k1 k2 regular, and not connected. The largest eigenvalue is k1, k2, and all the eigenvalues are between minus k1, k2, and k1. Okay? And therefore, the largest eigenvalue. Now we are talking all the time about symmetric matrix, so we can diagonalize it, and so if the eigenvalues of A square, if I know it, then I know the eigenvalues of A. The largest eigenvalue of A is square root of k1, k2. Okay, that's what we promised before. The other thing I promised is that it's symmetric, and here the proof is exactly the same as before. Just think about this in the following way, and you'll see that this is exactly the same. Proof of 2. If f is an eigenfunction of A with eigenvalue lambda, AF lambda f, then you can take f bar of V to be equal to f of v if v is in v1 and minus f of v if v is in v2, and then exactly as before, even though it's not, you can check, and then a of f bar is minus lambda f bar. So we see that the spectrum is symmetric in this case. So if square root of k1 k2 is an eigenvalue, then minus square root of k1, k2 is also an eigenvalue. And actually, why don't we even write, we will need it soon, so why don't we even write what are the eigenfunctions for these two eigenvalues? What is the let's be careful here. What is the eigenfunction? Maybe I will edit as number 3 here. So it will repeat. I'm sorry that I'm not so well organized today. I was just landing this morning and came here right away from the airport, and I already had to teach a class from 9 to 10. So I prepared the class, but on the airplane. So it maybe looks a little bit like that. So look at what is the eigenfunction of square root of k1, k2 is the following: is f of x is equal to let's see. I think it should be one. Should be 1 over square root, I think, of twice the size of V1.
K.
What?
1 over square root of.
Okay. Here is a normalizing. Okay, without okay, let's not normalize it now. Okay, so it's what, 1 over k1 or square root of k1? What?
Yes.
Without 2. This is if x is in V1, and 1 over square root of k2 if x is in V2. So it's constant. It's constant on each side, but it's not a constant function altogether. Okay, just let's check what is a of f of x. Let's say if x is in V1. This is equal, you sum over all its neighbors. All its neighbors are from the other side. And it has k1 neighbors, so it's equal k1 times the value in the other side, which is 1 over k2. No, so it's not good. So
switch the K1 and K2.
what?
Switch the K1 and K2 at the definition of that.
So here it should be k2. And here it should be k1. So this is equal to square root of k1, which is equal to square root of k1, k2 times 1 over square root of k2. So which means that this is equal to square root of k1, k2 times f of x. This is if x is in V1. And similarly, now this is symmetric. This is, and for x in V2, a of f of x will be k2 and 1 over square root of k2. So you see, this is the right definition, which gives you. We also square root of k1, square root of k2. Okay, so So these are the eigenfunction. Let's see. Maybe it's maybe I'll just write the theorem and then I want to prove today and then we'll take a break. So I'll keep this, I'm in this situation, and the theorem, which will be kind of a mixing lemma, is again x is v1 union v2 e bi-partite bi-regular k1 and k2 bi-regular as before, and denote and say and connected. I don't want to worry about the non-connected case. Denote lambda, the maximum of the eigenvalue lambda, lambda eigenvalue, and lambda is not square root of k1, k2. So we are really talking about the second largest eigenvalue. And then, if the claim is that if A is a subset of B1 and B is a subset of B2, then EAB, this is the edges, the number of edges between A and B. EAB is the set of edges, and then the number of edges from EAB minus square root of K1, K2 times A times B divided by square root of B1, B2 is at most lambda square root A square root B. Maybe, well, I don't know why I'm writing it this way. Maybe let me write it also in a different way, which will be slightly more intuitive. Another way to write it, note that what do we know? We know that K1 times V1. Okay, sometimes when I write V1, you understand. I mean the size of V1, of course, right? This is a set. So I will not carry all the time. K1 V1 is equal to K2 V2. So I really can write it like that. Also, so and the total number of edges, is the total number between V1 and V2 is equal to each one of them. K1, V1, which is also K2, V2. Then I can divide, if I divide it and I say EAB divided by E, which is like, what's the proportion of edges between A and B? So what we should expect? If it would be like a random graph, then we say there is the total number of edges is E. If everything will be kind of a fair share between the sets, then we would expect that I'm going out from A right, to the other side. How many edges are going to the other side? K1 times A. How many of them will go to B? Out of these, I expect that the number of them that will fall into B will be B over V2. Right? This is like what we want to expect if it will behave like a random. Or, if you want to think a bit in the other way, it will be K2 coming out of B, and how many of them will go to A? It will be A over V1. But this is okay because K1 over V1 over V2 is equal to K2 over V1. Right? K1 over V2 is equal to K2 over V1. So this is what we would expect if things will behave like random. So now I'm saying, let's see what happened there. If I divide EAB by K1 V1, that's what I did it. So I have divided this by K1 V1. So then I'm going to get minus, okay, let's do 1 over now what I want to say, I divided, K1 V1 times square root of K1 K2 divided by square root of V1 V2. So let's see, what is this? This is equal.
Forgot A and B.
What?
Forgot A and B.
I forgot A and B. A and B. So this is the same as EAB over E. And now K1 divided by K1.
Alex,
Yeah.
it would be easier to take, instead of dividing it by K1 and V1, take square root of K1 V1 times square root of K2 V2, and then
Okay, I understand this. I understand. Okay. K1 V1 is equal to K2 V2. So I will write it square root of K1 V1, square root of K2 V2. Right? This is equal, the product of them is equal to E. Thank you. Okay. So now square root of K1 goes out with square root of K1. Square root of K2 goes with square root of K2. And what we got here, so this is minus A over V1 times B over V2, which is really, okay, I didn't have to do that. It's really asking what is the fair share. What is the fair share of the edges from A to B? What is the proportion? Like this is the total number of edges. EAB is the number of edges going from A to B. If this would be a random situation, then the fair share, that the proportion of edges between A and B will be equal to the size of A divided by B, 1 times the size of B divided by V2, right? That will be the right proportion. And the proposition tells us that this is at most lambda, now we have to divide by the same thing, right? Lambda of what? Square root of A, B divided by square root of K1, V1, square root of K2, V2. So this is at most lambda, what we have here, A divided by, so it's like square root of A divided by V1, B divided by V2, and then all this is divided by square root of K1, K2. Okay, whatever it is, we'll go and study this after the break, but we see that this gives us the so-called discrepancy from the randomness. Like we have here a way to evaluate, and the crucial number is this lambda. This lambda gives us a way to evaluate what's the difference between the random distribution of edges to the actual distribution of edges. So if lambda is very, very small, if the graph is very, very good, now you remember that, look at this. We have lambda divided by square root of k1, k2, right? Square root of k1, k2, this is the largest eigenvalue. If this lambda divided by the largest eigenvalue is very small, if it's kind of a Ramanujan graph, if you know what is a Ramanujan graph, the second largest eigenvalue is much smaller than the largest eigenvalue, then this discrepancy will be very small, and it's kind of a square root of this type of this product. Okay? This is just kind of, we will prove, I think, we will prove it in this form, but I want to show you what is the real meaning of this inequality. Okay, I'll prove it after the break, it won't take